So this is largely based on this work with Olivia, who is here, and Masha, and Robert. Also, I'll have a slide on some work we did last year with LIGO experts, Lily and her student Spencer, who led this work, on future prospects of gravitational waves from scalar superradiance. Okay, so ultralight scalar fields is the BSM particles I will be looking at for. So why are they interesting? Just a very quick motivation. The QCD axion is one of the most well-motivated BSM particles from a particle physics perspective, in the sense that it solves a problem. It solves the strong CP problem of the strong interactions. This problem is roughly why do strong interactions seem to conserve CP. And in general, high UV completions of the standard model, such as string theory, in general can predict many ultralight particles. These come from the complex topology of the extra dimensions that you're compactifying to go from whatever 11 dimensions to our 4D universe. And they can have naturally suppressed masses. Now, a general feature of all these ultralight scalar particles is that they come with some potential. So usually, even if you're talking about string axioverse axions, you get some instaton contributions that give you cosine potential. And in general, you can expand any potential around the symmetric minimum, and you find that the first order term is a phi to the fourth term, a first order correction to the mass term, which is phi squared. I'll tell you more about the high order terms if you're interested later, but mostly I'm going to focus on this potential here. And I argue that it's an exhaustive study in terms of attractive potentials, what I'll be showing you. This lambda, this dimensionless number here, I'm going to write it just to establish some notation as the mass of the particle squared over some other scale squared, which I'm going to call the decay constant of the axion. This is just to connect to the QCD axion where these two things are related. So for the QCD axion, because the mu squared times f squared is set by lambda QCD, the two things are related. And for the particles that I'm going to talk about, which are comparable to radii of black holes, the masses are about 10 to the minus 12 eV, 10 to the minus 11, to 10 to the minus 13, roughly. And this corresponds for the QCD axion to decay constants of Planck to GATT scale. So Planck scale is 10 to the 19 GeV, so very high decay constant axions. For generic axions that come from string theory, these two numbers don't need to be related. So in principle, you have a 2D parameter space. Okay, so how do you spin down a black hole? So let's start with a black hole who is rotating at some frequency omega. And let's say that I want to scatter a wave which has some non-zero angular momentum, some dimensionless, azimuthal number, let's say it's 1, and some frequency omega. So if a kinematic condition is satisfied, which is that the frequency of this wave is less than the rotational frequency of the black hole, you get superradiance scattering. So the outgoing wave extracts angular momentum from the black hole, and the amplitude of this wave goes up. This is a very old effect described by Zeldovich and Starobinsky in the 70s for the first time. And it's a way to extract energy, and mostly angular momentum from the black hole. This is not a resonance condition, it's a kinematic condition. So whenever this condition is satisfied for the incoming wave, you get this instability. Or in this case, this superradiance scattering. Now, the reason why you can get growth, so an enhanced number of particles, is because you have an absorbing horizon. So there is a non-unitarity in your problem, which has to do with that everything has to be ingoing at the black hole's horizon. So now, if you take this black hole and you put it in a well, or in other words, if you have some particle which has some mass, then there is a Newtonian potential between the particle of mass mu and the black hole, and this particle mu can be bound around the black hole, just Kepler. So if the black hole is rotating, now this amplification of waves can happen continuously, because you are emitting particles into this well, and these particles help you take more energy away from the black hole due to usual Bose enhancement. So after some time, you build up a cloud around the black hole, which has extracted a lot of energy from the black hole. So this is a runaway process, in principle, at short times, until it back reacts on the black hole. So the fact that it has back reacted on the black hole tells you that the energy density that you have in this cloud is enormous. If you convert, so you extract roughly 10% of the energy of the black hole, and if you convert this energy density to units that you are more familiar with, it's about a white dwarf's density, sitting just around black holes. So the fact that we have such large energy densities around black holes tells you is essentially the reason why this thing can have imported signatures. So this I'm going to call the fine structure constant. That is the mass of the axion times the mass of the black hole times g Newton. And if you solve this problem, which is essentially a Schrödinger equation with a difference, because the potential is like a Coulomb potential, it's roughly the hydrogen problem, with the only difference that the horizon here is non-unitary. It has some ingoing boundary condition. So if you solve this problem, you find that your energy levels are kind of quantized. They can be described by NLM, the usual hydrogenic energy numbers. The energy is hydrogenic. It's alpha squared over n squared. And the cloud sits at the Bohr radius just like the electron sits around the hydrogen atom. The alphas that I'm going to talk about are in this range, so roughly less than 1. If you go to alphas very, very small, you just don't grow these clouds because these growth rates that you see here are very suppressed functions of this alpha. And this suppression has to do with how much these wave functions overlap with the horizon. So I'm going to refer to these levels as the hydrogenic energy levels NLM. And basically, for everything I'm going to talk about, it will be the 2, 1, 1, and 3 to 2 that are relevant. So the smallest, the ones that are closest to the black hole and have the largest angular momentum, the smallest angular momentum. So some key aspects, just to go through them. It's the non-hermiticity that leads to this particle creation. And we create these gravitational atoms around black holes due to this process. Now, the most interesting aspect of superradiance is that it's completely independent of any pre-existing abundance. So you don't have to rely on this particle being the dark matter or having any astrophysical abundance. It can just grow spontaneously from quantum fluctuations. Because in other words, it's saying that if this particle exists in your theory, black hole spacetimes that are rotating fast enough are unstable to the growth of these clouds. And there is a huge energy density that we will take advantage of for signatures. So just to remind to you, those of you who know, and explain to the rest of you what happens if you have no self-interactions, the simple story. So imagine, described for the first time by Mina, Savas, and collaborators, and later by Mina and Sergei, etc. So imagine that you have a black hole born after some merger, let's say, with some high spin, 0.9 in this dimensionless number, where the maximum is 1, with, let's say, 40 solar masses, at 40 solar masses. These contours, these blue regions here, show you where these growth rates are positive, so where you can get this instability to grow. In principle, if you had infinite time, this would go all the way down to 0. At some point, we have them turn up in this diagram. This is actually from a paper of Mina and Masha and Sinlu. They go up because other astrophysical timescales become important, and things, black holes can, the spin can go up again, and you have other things competing with superradiance. So essentially, superradiance can grow only in the blue regions. So you compute the timescale to grow the first level. You find it's about a year. So what happens is you start growing this level, and the number grows from essentially 1/2, which is quantum fluctuations, to 10 to the 78. And once your level has grown, it has back react on the black hole, so you get this step function in the spin. You've extracted the angular momentum, and you've put it in this cloud around the black hole. Now notice that this is 10 to the 78, starting from 1/2. So there are actually many e-folds. It's not just the rate, the growth rate that you compute. It's also about 180 times this rate to reach from 1/2 to 10 to the 78. And this will become important in a few slides. But in any case, the level has grown. It stays there for some time. And because it's a 2-1-1 level, it has angular momentum. It has an oscillating quadruple, oscillating at the mass of the particle. So you get gravitational wave emission, which is both a signature, but also makes the cloud decay slowly. It's a parallel decay in time. It does nothing to the black hole, so the black hole spin just stays there while this thing is decaying. And after some time, which is parametrically longer, the next level will grow. And it's about 10 to the 6 years for this choice of parameters, so much, much longer. And what happens is a hierarchical sort of dynamics where you grow the first level, it decays to gravitational waves, then you grow the second level, it will again decay to gravitational waves sometime later, and you get this step function in the black hole spin. And the previous level, because now you've spun down the black hole even more, not only is this thing not super radiating anymore, it becomes unstable. It falls back into the black hole. The superradiant condition I showed you in a few slides earlier becomes such that these interaction rates are negative. Growth rates are negative. But in principle, you want to put any signatures that you have or any constraints that you have in this 2D parameter space that we usually think about in particle physics, which is the mass and the coupling constant. Now, this parameter space in particular has to do with the coupling of the action to the standard model. For superradiance, while this scale, I'll assume it's the same scale of the self-interactions, it doesn't have to be. So this particle, in principle, can only couple to gravity and to itself, and not to any standard model particle. But if you're thinking about any of these other actions that we look with experiments, or that we think of in astrophysics, producing stars, supernova, etc., there is also a coupling to the standard model that roughly comes at the same scale. OK, so that's what we did in our paper. So the self-interactions were discussed from the very first paper, the Axiverse paper, and the next paper by Mina and Sergey. They thought at the time that some violent thing is happening. You grow these clouds. They have huge attractive interactions, and they collapse due to their own attractive self-interactions. Later, Andrei pointed out that through a toy model that in principle, that in general, you may get quasi-equilibria before you reach these violent regions. And we did some essentially exhaustive study of the parameter space to verify what is happening. And you can think of these self-interactions, this phi to the fourth, as a quasi-Feynman-like diagram, where you get these 4 legs, because it's a phi to the fourth, and each leg has a different level. Essentially, two levels interacting, giving you 2 other levels. There are other configurations of this diagram I can tell you if you're interested in, but this is going to be the important one, 2 in the initial state, 2 in the final state. And qualitatively, what we found is that you produce new quasi-equilibria, and that this hierarchical growth and decay of levels is no longer the case. So the important processes are the following. As you're building the first level, 2, 1, 1, through superradiance, nothing happens, because this phi to the fourth is a much smaller potential compared to the mass. So initially, you just grow the first level through superradiance. As this level has a significant occupation number, this process to move energy from the lower level to the higher level becomes significant. So now, because of this, of the growth of this level and the self-interactions, you put particles in the higher level, the 3 to 2. Because you need to conserve angular momentum, the other level is unbound. So already you have a process that puts axions to the higher level and also throws some of them back into the black hole. As this process continues, the opposite can happen, the back reaction, which is 2 particles from the higher level going back to the previous level. And if you compute the other leg of this diagram here, you find that it's an unbound radiation. So you get, on top of gravitational waves, you get also axion waves from this process here. The black hole becomes a beacon of axions that, in fact, you can look with experiments on Earth, but I'm not going to go into details about that in this talk. But you can ask me if you're interested. So when you have these energy exchange processes, and as you see, because there is the action and the back reaction in a sense, it makes sense that you get some equilibrium or quasi-equilibrium, because you always have some decay channel to remove energy from the system. So let me show you the parameter space. So these are the masses of the actions that are relevant for black hole superradiance, in the sense that anything with smaller masses essentially doesn't grow in the age of the universe, or in fact in the astrophysical ages of black holes. And this is the decay constant. Strong self-interactions are up here. So if you wanted to put the standard model constraints on this FA, assuming it's the same with 4 self-interactions and the standard model interactions, astrophysical constraints would be somewhere around here, up here. But essentially, this whole thing is open. We map out, in this work, we map out this entire parameter space that you see here. And I can tell you what this multi-level thing is. I'm not going to go into any details, but essentially we cannot say much here because our analytics break down. So let me describe to you what is happening as you start from very small self-interactions here, or let's say Planck scale, which is this thing here, and you go to higher, smaller phase and larger self-interactions. The first thing that happens is gravitational superradiance, the story I showed you just now. And right after that, you get some early growth of the second level because of the first process, that you can remove particles from the first level and put them in the next level. So in time, here I'm showing you the normalized occupation number, normalized to 1. So this would be 10 to the 78 in actual particle number as a function of time. So what you get is the dark line here is the line I showed you earlier. The solid line is 211. It grows, decays to gravitational waves, and at some point, the next level grows 3 to 2. It will decay to gravitational waves, and the previous level becomes unstable and falls back. As you crank up self-interactions, nothing happens initially to 211, but at some time later, this self-interaction process becomes significant, and you start populating the previous level. So you see it would have grown in 10 to the 7 years, but through self-interactions, I grow to 100 years. I remove energy from the system because I also radiate to infinity, and I get this quasi-equilibrium where both levels are occupied at parametrically slightly different occupation numbers, and they both decay to gravitational waves and axion waves during this stage here. Now, a cute thing that happens in this regime is that I told you need almost 200 e-folds to grow from vacuum fluctuations through superradiance. So the growth rate, where you would grow 3 to 2, the next level to the max occupation, is 200 the growth rate. But I start with a previous occupation. I start with 10 to the minus 2 of the maximum. So these 200 e-folds are irrelevant now. I can grow from a pre-existing population to the max much earlier. So I spin down the black hole much earlier than I would have thought from just the naive gravitational story. And it decays to gravitational waves, et cetera, et cetera. The next thing that happens after you have this early growth of 3 to 2 is you start affecting 211 itself. It doesn't reach its maximum occupation. This is what happens here. And in time, it looks like this. Instead of reaching 1 up here, you reach something like 10 to the minus 6. And the previous level, because self-interactions are so strong, grows at essentially the same time, which is the reason why this doesn't grow to its maximum. They back-react almost immediately. And you can get this time here where you get an almost equilibrium, where both levels essentially remain at the same occupation number for some time. The reason why is because they have such a small occupation number, all decay processes become inefficient because they are all proportional to the number of particles in the system. And you see this more prominent here, where the maximum occupation number of this level is so much suppressed that all the decay processes are very, very suppressed, and you get this equilibrium for a very long time, almost a billion years here. So you can already see from these things I showed you that signatures that you would think superradiance has, such as gravitational waves, get suppressed as you go to higher phase because your clouds are smaller. So the energy density in these things is just smaller to give you the loud signatures in gravitational wave detectors. So let's see how this looks like. This is how the spin evolves. I'm going to skip it for the interest of time. So let me talk about signatures in the last 5 minutes. You get annihilation signatures as you did in gravitational superradiance. The cloud just has a quadrupole. It oscillates and emits gravitational waves. You can think of this as basically 2 axions giving you 1 gravitational wave at a frequency of twice the axion mass. But new signatures that we can have if we have 2 levels occupied are transition signatures. So you can have, similar to the electron, going to a lower level in the hydrogen atom and emitting a photon. Here you can have an axion from the higher level emitting a graviton and going to the lower level. And there is a parametric difference between the frequency of this thing and the frequency of this thing. So because the mass of the axion is comparable to the mass of the black hole, which is what LIGO is built to search for, these axions, these gravitational waves are perfect for a detector like LIGO. These gravitational waves don't have the mass, but have the Bohr radius, or the binding energy. So the frequency is much smaller, parametrically smaller. And the frequency of these waves is about 100 to 1,000 times smaller than this one. So you have to go to future detectors in space to look for this signal here. But it is a new signature. And I'll show you a slide about this. We also get action waves, which is a BSM signal that we can look for on Earth, but I'm not going to talk about this. And spin-down constraints that I'm going to explain for those of you who don't know what they are briefly, get modified. And these are also modified. So let's see how the annihilations are modified, right? I told you that essentially, again, this is FA, this is the mass essentially is here, or the fine structure constant, the mass is up here. For some black hole at some distance of 1 kiloparsec, what is the peak strain that you get on Earth? So while if you don't change the maximum occupation number of the cloud, the peak signal doesn't change. So as you see here, until I reach this region C, which is where I start back reacting on the maximum occupation of the first level, these are essentially straight lines. So the peak strain doesn't care about FA until I reach this region here. And here, these things become suppressed. However, the signatures that you expect are not necessarily the same down here, because the time that you spend at the peak signal is different. So once you go, while you modify the peak signal up here, down here, you modify the time during which the cloud remains at this peak signal, because you get this extra decay channel to actions, to infinity. So you see that by the time you reach this region up here, you've reduced the peak time by 5, 6 orders of magnitude. And if you're doing a blind search, so let's say you look, if you're doing a targeted search, let's say you look at Cygnus X1, assume it has a low spin and emits gravitational waves from a cloud, this doesn't really matter. But if you're doing a blind search, this matters because the fraction of time every black hole in your population study spends at the peak signal time is suppressed. So your total event rate gets suppressed by this fraction. And this is what I show you here. This is some observable signals as a function of the axion mass for LIGO. And you see that if you have essentially Planck scale decay constant, you get the expectation of gravitational superradiance, which is hundreds to thousands of events that are many papers talking about. But the moment you make this just an order of magnitude larger, still in the regime where 211 grows to its maximum occupation, you get an order of magnitude suppression. You slightly suppress it even more, and it's completely gone. It's 10 to the minus 1 signals. So for blind searches, self-interactions can be important even for not such strong self-interactions. Here, I'm showing you some expected gravitational detector reach for a targeted search on, let's say, Cygnus X1, assuming it has a cloud around it. It has grown a cloud around, and the spin is small, 0.99. This is 3-to-2 annihilations, annihilations from the higher level. These are irrelevant. I just want to show you here. This is the expected reach of advanced LIGO. This is the green thing here, and some constraints from previous searches. And future telescopes, such as the Einstein telescope and Cosmic Explorer, which are here, red and black, they're essentially overlaid, can probe the regime where you get some of these self-interactions. So despite the fact that your cloud spends a little bit less time in this peak signal, these detectors will be strong enough to see this. And the very cute thing is that at the same time that you get this signal, you get the transition signal as well, because both clouds are occupied now. And space detectors such as DESIGO would be able to pick up the signal, as you see here, at the frequencies that are 100 to 1,000 times smaller than what LIGO's is. So you get some sort of axion multi-messenger signal where you can you see the same signal twice the mass and at the binding energy. And this would help you distinguish through astrophysical backgrounds. So I'm out of time. I'm not going to talk about the constraints, but you can put constraints. Essentially, when you don't spin down these black holes anymore because these clouds are small, you don't constrain particles anymore. You can ask more if you're interested. Come on. And just to recap, I hope I convinced you, self-interactions dramatically affect the evolution of the cloud. We get these both annihilations and transitions, which future detectors will be able to see. Spin down constraints are modified. I didn't have time to talk about it, and I also didn't have time to talk about this, but I think this is also interesting, and thank you for your attention. Take any questions.
Questions for Marius?
Nice talk. So you mentioned about axiverse. So you may expect like multiple axions in the similar spectrum. If they talk with each other, would that modify your story significantly?
Well, depends how they talk to each other, what is
Mass
the
mixing
scale of
or
this
something like
interaction. Depends on a lot of things. So if they talk and the masses are accidentally similar, okay, so if let's say they don't talk to each other at all, the first thing you would grow would be the axion with a higher, and assuming both, okay, it's a bit complicated, right? So assuming both of them superradiate, okay, the thing that you will grow first is the thing with the higher mass because it has a higher growth rate, assuming the first level that grows is the first, okay? So you will spin down the black hole before you have time to grow the other one, and which will still be superradiating, right? So then you will build the other one. Now, if they have some interaction rate, indeed, you can, presumably, I can expect you will have interactions between these two clouds. But I don't know exactly how, I mean, there will be a hierarchy of timescales. How strong are the self-interactions of the cloud itself compared to the interactions between the axions? So that's something that someone needs to work out. If not, it's also, it could be that one of them doesn't superradiate, in which case probably nothing will happen. I think so. It will be the same story. But yeah, this is not something I thought about.
Can you comment on the sensitivity of the constraints to the black hole spin measurement? Like, well, or like, are these aren't LIGO? These aren't based on LIGO measurements, right?
Right. So these constraints are set in the following way. You're saying, if this axion existed during the astrophysical time of some black hole that we've seen, given that we observe this black hole with a high spin, an axion there would have spun down this black hole, so we wouldn't see this high spin now. So these constraints have to do with the measured spins of these X-ray binaries, and whether you can place a constraint. And all these binaries are supposed to have high spins. So if you don't trust the high spin measurements, then these constraints are not there, and or are suppressed or whatever would be modified because these assume the highest spins.
What is the tolerance? Like, at what spin measurement? If they said it's instead of 0.99, it's 0.7 or 0.6. At what point does the?
Yeah, it could be roughly on very broad strokes, unless you're near threshold for the superradiant level to grow. Where is it? It would be something like the threshold for the 211. Where is it? Sorry, here. The slide I skipped. Sorry, you're going to see the whole thing. Okay, here. There, okay. So the threshold for the 211 would be something like 0.65 or something. So if the spin was below here, you wouldn't grow this level.
Okay, I see.
Yeah. Okay. And as long as you're not near this threshold, it's roughly the same, even if it was 0.99 compared to, let's say, 0.7. Roughly.
Any more questions? Yeah.
Up here?
Yes, I just want to understand how to understand this more stable situation. I mean, a lower FA looks like a smaller coupling constant.
No, it's larger because the coupling goes like 1 over FA.
Yeah. Oh, sorry. So that's a stronger coupling constant, but then why that makes it more stable?
Oh, right. So you get what happens. Yeah, it's the inverse process that happens in superradiance. If you have nothing, the entire thing will grow to its maximum occupation. As you start cranking up the self-interaction of the levels itself, you open up new decay channels that take axions away and just radiate them to infinity. So
The smaller coupling constant makes it easier to decay.
exactly, which just equilibrates to a lower occupation number, but it reaches an equilibrium. Sure, you radiate to infinity. It's an efficient radiator of axions. But it's the equilibrium that matters, because it's many processes that happen. So the black hole always superradiates. The black hole always puts energy in the system. It's just that the system, at these occupation numbers, is very efficient at taking all the energy from the black hole and radiating it to infinity. So it's stationary, but energy exchange is continuously happening.
Quick question.
Can you say, like, I don't know, 20 words about detecting those radiated axions in Earth-based detectors?
Yeah. OK, this is somewhere in my 40 backup slides, which unfortunately I cannot scroll, like quickly scroll to. I'm already past that. So in principle, you can look for these axions in Earth-based experiments that look for QCD axion dark matter, or ALP dark matter. The key point is you have very, very low occupation numbers, but the way the cloud is smaller compared to the maximum is, you work it out, it's FA squared, it's this decay coupling squared. But the coupling to a spin, let's say, if this had the standard model coupling, scales exactly the same, but stronger. So despite the fact that these things become smaller, their interaction on Earth becomes larger. So in this regime, they compensate each other. So you always get some signal on Earth. The problem is these black holes are far. So if you convert this to an energy density, something like 10 to the minus 5 of the dark matter density, so it's more suppressed than the dark matter that this experiment would be sensitive to. Still, you can look for them. We have some rough sensitivity, which is buried somewhere here. You can ask me later. But we're also thinking of ways that will be forthcoming very recently, very, I think in the next month, where you can probably enhance the sensitivity of these experiments and have a more interesting science case for these actions. More than 20 words, but yeah.
Okay, great.